Some of the Big Bang Theory's validity is being questioned in light of new data. The James Webb Space Telescope found it. We recently created a surprising discovery with this telescope, one that is changing the world of physics. The most recent image taken by the telescope has produced persuasive arguments that caught experts off guard, is putting a stop to much speculation. The most recent find made by the telescope is visually stunning and has the potential to change our comprehension of the universe. Experts. Discussions regarding this image have revolved around the perception of the universe. The stunning photograph, taken by the James Webb Space Telescope, challenges our understanding of the cosmos. This finding provides an answer to one of the primary issues in astrophysics: the age of the universe and the rate at which it is expanding. Researchers from various generations have been left perplexed by this unsolved phenomenon and have carried out many studies in search of answers. Cosmologists study how the universe began, how it works, how it has evolved over time, and how it might end. Significant advances have been made in this field over the past century. The most widely accepted cosmological theory is the Big Bang theory, which holds that the universe began about 13.8 billion years ago, starting from a dense and extremely hot state. The Hubble constant specifies the rate at which the universe is expanding. However, measuring the Hubble constant is difficult. There are two primary methods of measurement. The first involves local measurements, including observations of early universe objects in space, such as stars and type Ia supernova, which are used as standard candles. Their constant brightness allows astronomers to determine their distances and, as a result, calculate the Hubble constant. Over time, scientists have been able to refine this method. The second approach uses measurements of the early universe by studying the cosmic microwave background, CMB radiation. Discovered in the 1960s, the CMB is the afterglow of the Big Bang. Microwave energy was generated when the universe was just 380,000 years old. By observing tiny ripples in temperature and polarization released by the CMB, astronomers can determine the age of the universe and the rate of its expansion. However, there is a problem. These methods don't yield the same results. Local measurements suggest the universe is expanding at a faster rate than what CMB data suggests. Scientists have been working hard to understand why the outcomes vary, trying to decipher additional mysteries of the cosmos. These discrepancies indicate that we still have much to learn. There may be errors in one or both approaches. Fortunately, thanks to the James Webb Space Telescope, we can peer deeper into space than ever before, revealing galaxies and planets once unimaginable. Researchers hope the telescope's data would help determine the Hubble constant more accurately. However, the first set of findings contradicted prior expectations. Could this new information give us insight into the universe that forces us to reevaluate how we understand it? We may uncover previously unknown forces or particles, or we may discover that the mysterious force known as dark energy, which accelerates the universe's expansion, must be rethought. With every new discovery, our concept of space evolves. For example, the 1965 discovery of the cosmic microwave background provided compelling support for the Big Bang theory. Before that, many scientists believed the universe would continue expanding at a constant rate indefinitely. But in the late 1990s, it was discovered that the expansion rate is actually accelerating. A major clue about the effects of dark energy. Every time we make a new discovery, we test how well it fits with what we already know and explore new ways to understand the universe. Without this process, the challenges in cosmology might not lead to better understanding. Despite the complexity, this issue is exciting. It inspires scientific growth and innovation in instrumentation. Scientists around the world are drawn to this mystery, eager to learn more about the universe, a testament to how science is always changing as we gain new knowledge. Another concept that goes hand in hand with Hubble tension is the structure and age of the universe. Tension refers to the way matter is distributed in space. Scientists use data to simulate the universe's structure and study how it has evolved. Over time, certain regions of space have become dense with galaxies, while others remain mostly empty. Scientists use various methods to assess how this distribution affects our understanding. One approach is to observe how matter density, such as a galaxy cluster, bends light, a phenomenon known as gravitational lensing. This helps reveal the effects of dark matter, which does not emit light and is thus undetectable through traditional means. Researchers also study the CMB, cosmic microwave background, which carries the universe's ancient afterglow. This light has been traveling for about 13.8 billion years and carries information from the universe's earliest moments. By analyzing the CMB, scientists can understand how the universe was filled with tiny anomalies at its formation. However, this information does not fully align with the large-scale irregularities observed today. The distribution of gravity, which is no longer spherical, suggests that the universe was more uniform in its early days than it is now. Viewed through the lens of gravity, this inconsistency implies that something fundamental is missing from our current models, once again bringing us back to the mystery of dark matter and its nature. Operates in accordance with he and his crew were able to rise. The Webb has allowed them to rethink their work, the Space Telescope, and the desire to examine whether a potential error in the Hubble Space Telescope's measurements might be too. Blame for this discrepancy prompted investigation. But the JWST revealed the same deviations, which are concerning. Somewhere in the middle of the two observations, our comprehension of the universe must have a fundamental flaw. Rice stated in a conversation with an astronomy publication in the United States, employing our new space telescope has made it possible to take a deeper look at the universe. Through its clear infrared view, an investigation of cosmic distances with ever greater accuracy, dark energy and dark matter are mysterious parts that make up an important portion of the universe. But despite being black, their nature remains elusive. Black holes have been the leading explanation for particular gravitational effects. There is increasing interest in determining how dark energy and dark matter could have an impact on these cosmic phenomena. Please share your thoughts in the box provided. If you enjoy the video, please like and subscribe, and many thanks for watching. I hope to see you again in the next one. You, as scientists, keep looking at the James Webb Space Telescope's data. The fundamentals of contemporary cosmology are the subject of unprecedented scrutiny. The capacity of a telescope to observe distant galaxies, just a few 100 million years old, formed shortly after the Big Bang, presents problems for existing models of how galaxies form. Contrary to previous beliefs, it appears that the early universe hosted more, larger, and more mature galaxies than anticipated. Based on these findings, either galaxy formation happened much more quickly than we previously thought, or our comprehension of the underlying physics of the early universe requires a fundamental amendment. One emerging theory to explain these differences includes changes made to the lambda CDM model, the current prevailing cosmological model. This includes CDM cold dark matter and lambda, a cosmological constant illustrating dark energy. A few physicists suggest that dark energy might not be constant at all, but may instead fluctuate or interact with dark matter over time. This constantly changing form of dark energy, sometimes called quintessence, may provide an explanation for the varying rates of cosmic expansion observed in various epochs. Other researchers are looking into modified gravity models. For example, dynamic Mond-modified Newtonian dynamics, or scalar tensor theories that call for modifications to Einstein's general theory of relativity. These hypotheses, which hold up on cosmological scales, endeavor to explain phenomena such as the formation and gravitational lensing of the structure of the universe without using entities such as dark matter or dark energy. Despite their controversy, these ideas are gaining attention and emphasize the increasing willingness to call into question long-held assumptions based on new data. Additionally, the JWST's observational data has opened up possibilities for studying the atmospheres and chemical makeup of exoplanets, some of which orbit within their star's habitable zones. These studies may not directly affect our comprehension of cosmic expansion. However, they provide useful context for star system evolution and the possibility of universe-wide life. JWST's discovery of chemical fingerprints in these environments may also provide clues. Regarding the wider spread of elements across the universe, another important component of the cosmology puzzle is the behavior and nature of inflation. A very rapid expansion of the universe, believed to have occurred just a few milliseconds after the Big Bang. The inflationary model helps explain why the universe appears uniform across vast areas, despite the immense distances between them. But the precise mechanism behind inflation is unknown. Various speculative models exist, including those involving scalar fields and quantum fluctuations. However, no theory has yet been validated by observational evidence. The most recent data from the James Webb Space Telescope may provide fresh perspectives on the inflationary epoch by examining the distribution and structure of the earliest galaxies. Researchers hope to uncover patterns that either support specific inflation models or refute them. In the event that anomalies such as irregularities or unexpected clustering are seen in the cosmic background, they could point to physics that go beyond the standard model. In parallel, theoretical physicists are attempting to unite quantum mechanics with general relativity, a problem that remains one of the greatest challenges in modern science. A successful quantum gravity theory could fundamentally alter our comprehension of the universe's origins, including the moment of the Big Bang itself. There are two major approaches: string theory and loop quantum gravity. Both, however, remain highly speculative due to a lack of direct experimental support. All of these efforts, whether observational or theoretical, point to a single, unified truth. Our comprehension of the universe is still developing. The James Webb Space Telescope has not only made discoveries, but also provided us with the tools to refine our questions as more data is collected, particularly from long-duration missions and complementary tools like the Euclid Space Telescope, or ground-based observatories like the Vera Rubin Observatory. We may soon find ourselves on the verge of a brand new cosmological paradigm. Until then, the conflict between various measurements of the universe's expansion and the significant repercussions of those differences will continue to drive debate and discovery in the scientific community. What lies beyond may not only alter our comprehension of the universe, but also its history and future.